Okay, so what is topology? I've mentioned it in passing a couple of times. Does anybody remember topology from our readings? It's different than topography, so watch out for that trap. Yeah, so topology is rules about your geometry, and they're rules that are strictly enforcing the way that you draw a vector feature. And there's something that not all GIS systems and not even shapefiles necessarily follow. So they have their benefits, but also their costs. So something to keep in mind and understand how it can be to your advantage to follow the rules when you need them and ignore them when you don't. So they like to throw around this term spaghetti modeling for the way that vector features are generated when you don't follow the rules of topology. But then they draw this really nice square angular spaghetti, which I guess it's the uncooked spaghetti model. It's what would happen if you took your spaghetti and threw it on the floor before cooking it. You would have a lot of overlapping, unconnected, totally disjuncted, unrelated features. And if you are going to take this data, which clearly started out as point and line data, and try to do some sort of polygon analysis with it, which is a really common progression in your data analysis, then you would be at a loss here. In fact, this is kind of the story of my day. I got a new set of files from our engineers. I'm doing some analysis of wetland impacts on a project, and they send me everything in line files. And you guess what engineers don't do when they draw? They don't use snapping. So their lines don't connect, and their area features that they send me are not areas that you can't see the air quotes. They think they're doing something useful, and it takes me hours to repair it so that I can actually calculate an area from each of these little tiny slices that they've cut out. We'll also talk about slicing. That's another thing you can avoid with good topology. In order to get to the final goal, which is a calculation of the area that we're going to impact, so my client can pay for their wetland impacts. So there's definite consequences of ignoring topology and ignoring the tools that allow you to maintain good topology. So the general rules of topology is that you must have, I must have moved that one down, sorry. You must have no overlapping lines, and your polygon and line features have some information about adjacency, which tells you how the polygons are related. And we'll come back to the rest of that. So I might have flipped through this and given away the answer. How many polygons do we have here? Well, it depends on which system you're using. So if you're using a non-topologic system, you could describe this in a couple of different ways. You have either two overlapping squares, or you have two little Pac-Man features, both eating the inner square. So for spaghetti mapping, you can have multiple polygons. Each one is related to a record in the attribute table. If you're following the rules of topology, where you cannot have overlapping lines without a node at their intersection, then this is 3 features. So there's some interesting consequences for that. If I am trying to capture something that can have overlap, can't necessarily think of something off the top of my head, but if you have things that are not necessarily contradictory that you're trying to capture, and you're just enclosing them in areas, then it might make sense that they overlap. But if you are trying to calculated totality. I don't want to pay for more mitigation costs than there is land within my area, because that would be absurd. So what I want to do is capture that area in polygons and then break it into individual features that each has an attribute. So even though these might be overlapping, I'm only going to pay for this internal polygon once. That's the general mindset behind topology rules. So again, the initial or original spaghetti feature is a really basic one-to-one. You have points that are connected by lines that are enclosed into polygons. And there's no discussion of the relationships between those polygons. And the way that might look differently in a topology system is that you track some of the information that you use to generate those features. So you track the order in which you enter those points, and you track the relationship between the arcs that form your polygons. So there's some vocabulary that we've already brought up a little bit, but the start and end of your line or your arc is a node. The connection between those you can refer to as a line and a node, and one of the reasons that's helpful is understanding that you can represent this connection in different ways. Sometimes we do use curved lines when it's helpful, because the information carried by that line is not controlled by the points that it goes through. You only have nodes and vectors. So where you do not have nodes and vectors, you're somewhat free to imagine those at your whim. And you'll see that some playing with the symbology when you're trying to represent different polygons or lines in ArcGIS. So one of the consequences of this for the functionality of the software is, although you may not see what's happening behind the scenes to create these topology rules, you can use them to enforce rules while you're mapping. So it can help you avoid some obvious errors, or at least visually clear errors. Key ones being points that don't snap together. So in enforcement of the rules, you can't have overlapping, right? So here we have a non-planar line system where we have a node here and a node here, and presumably there are nodes at the other ends of these lines that we're connecting to. So we have lines crossing each other without intersecting nodes, which if you're following topology rules, the system won't allow you to do. It'll create a node at that intersection and therefore lock that into place. And then similarly with a polygon, you wouldn't have overlapping areas in a topology corrected system. You would have 3 different polygons, and the overlapping area would have its own features associated. So here's a really good visual representation of the errors that I commonly see in, especially in CAD files coming from people who don't enforce topology, that you would avoid by using topology rules. So slivers in between polygon features are really common when you're drawing your polygon and you're following a line that you've already created, and you're not snapping to the nodes along that line. It's really easy to end up with errors of overlap on either side. Polygons that don't close like these unsnapped nodes will result in you not being able to calculate area because it's not enclosed, so it's trying to do an infinite area calculation. And then between features, it's previously was not that uncommon to try to start on your next feature in your shapefile and have some connection remaining because you didn't actually pause. And that's the unended line here. And then there's everybody's favorite, the spike. And this is really common when you're importing, say, real survey data, and there's, for whatever reason, some rogue point in that system, maybe just like a extra data file entry that nobody knew was there, that's suddenly trying to connect back to 0, 0, and you end up with these funky lines. So there's some routines that we can run within Esri to control these kind of errors, and also within QGIS. All right, so there's a little bit of difference that happens on the back end of the file to help encode this geometry with the topology in mind. So we're no longer just capturing the coordinates and the attributes, we're also trying to connect how the coordinates relate to each other. So I think I'm gonna give you guys a break right there and come back to this, and we'll pick up on this slide. Does anybody have any questions so far about topology?
I have a question about the left and right columns.
Yeah.
How is it defining left versus a right poly?
So that gets back to the question, or the slide I showed earlier about how a polygon is enclosing in a specific direction. So depending on the order of your points that you've drawn, your polygon will be to your right.
Thank you.
Yeah. So the primary functional difference between the spaghetti system and the vector topology system is how the data is stored. So this gives you a little bit of an insight into what those storage models might look like, although there's probably a lot more binary information in there. And essentially what that's going to affect is how you're prevented from making errors, and that's going to vary a little bit from software to software, but something to be aware of and something to understand so that you can use it as the tool that it's intended to be. So we won't have any of that in our lab this week, but we'll try to make sure that we have something in one of the labs so you can see how that operates hands-on. So advantages and disadvantages of the spaghetti model. Like I said, it's fairly simple and it can be efficient. It's been around for a long time. There's not much to it. But the disadvantages is that it can allow errors into your data, and that it can cause editing problems for people down the road like me who end up with your error-ridden data and have to deal with and interpret that to the best of their ability. Versus the topology data model, it can actually cut down on storage for the spatial information, but you then have to store the topology information, so there's some trade-offs there depending on the size of your data set. But it maintains clean files without errors that can then be a lot more efficient when you're trying to do analysis that goes beyond the initial just drawing these objects. But it does take a little bit more time to create because you're following rules, which takes time. So the last piece of what we're going to talk about tonight is network models. And I don't know if we'll have any exercises on this in our lab, but is another piece of what GIS can give you, and a really valuable piece to industry, because this is how you generate huge efficiencies in real world systems from a GIS system. So basically what network modeling does is tell you the most efficient way to manage your network. And you can have a really wide variety of different networks. This could be a road network, this could be a network in a software system. This could be a network of infrastructure for a shipping system. It's a visual representation of a network, not necessarily an actual graphical network, though that's the most common in GIS systems, but can be used in a lot of different ways. And a lot of the methods behind it are similar whether or not there's geography involved. So you have connected features that are connected at centers. So the distribution center analogy is a really good one, or say you're serving out memory from a computer system, or trying to deploy a fleet of vehicles from a geographic point. Those would be your centers, and your network links are represented as your line geometry. And in a geospatial system, those would have vectors at intersections and turns to represent those lines. And then you'll have some sort of attributes that tell you how you can behave along those lines. So if you have a road system with one-way roads, it would give you the information that you can only travel a certain direction on those roads or certain speeds if you're trying to manage your fleet mobility. So any information about how you travel along those routes would be captured within the attributes of those lines or links. So we use these types of systems to answer real world questions, and they're incredibly useful because of it. So just a little hands-on exercise. If you can remember your, oh, I forgot to put the Pear Deck in. I can't check your responses. You'll have to throw something in chat or pipe up for me. But moving from point A to point B in a Euclidean system, you're traveling along a line. Hopefully you all remember Pythagorean theorem and how you would calculate a distance along a line. But moving along a network, you have to follow the rules of that network. So for the example that's shown, to get from point A to B, you have to notice that the lines are directional. So which would be further away, since I forgot Pear Deck and I can't make you do math? And which system would you travel further? Yeah, your network system. But that doesn't necessarily matter in a real world environment where you may not be able to travel the Euclidean route, right? So the only goal of this slide is to get you to recognize that there is some cost to the network system, in which case you're following the rules basically, but it's giving you the opportunity to model those rules. That slide keeps reappearing. So in a nutshell, what we covered today was rules of topology, tin systems, networks. Didn't really include in here the characteristics of a shapefile and the three types of data that we represent in shapefiles.